people coming. I expected only 1 or 2% coming, but we have a lot. So today I'm going to start talking about how to assume the sticky Kakeya theorem and prove the corresponding theorem for prove the Kakeya set conjecture in R3. So let me. So we are going to use this inductive statement. So we have this KKT beta, and so suppose a set of tubes satisfies the Kakeya-Wolff axiom. The maximal density is small, and also assuming this Kf beta means that suppose a set of tubes satisfies the Frossman-Wolff axiom, and then we have certain bound. The goal is to prove that the two statements hold for beta equals to 0. And the proof consists of two lemmas. The Kakeya version implies the Frossman version, and also and altogether they self-improve. So last time we said that to start with, we want to do induction scales, and then we decompose into those mu t. I will just ignore the shading for now. Is less than mu grain, and the grains are those delta over rho segment. And we said that we apply factoring. We apply factoring to the set of grains and obtain a collection of W's that is a convex set. So those are W's, and because we also need to understand. So this again, this mu will be decomposed as mu inside W and then mu W. So this is the factoring of multiplicity we said after the factoring proposition yesterday. So this is the idea. We bounded the multiplicity by this part we can apply induction, and this part we need to apply factoring proposition to find the corresponding W's, which are structures of the set. So this satisfies this Frossman is less than 1, and then this the maximal density of W is less than 1. So and this we can see that these are the very good object to apply our inductive hypothesis. And so in order to understand the multiplicity of W, because we don't have any, we cannot really predict the size or the corresponding dimensions of W. So this motivates us to understand the multiplicity of planks. So intersection of planks. That's the beginning of the topics. So the W's, we call them planks, means A times B times 1, and A is less than B less than 1. Usually A is, when we say it's a plank, usually means that A is much less than B and B is less than 1. So how do we get those information about intersection of planks from those two inductive statements? Also, I should say that the two statements, when beta equals to 1, this is trivial. So we have something we have a base case to start with. So to understand how planks intersect, we use those inductive statements for intersection of tubes. And so the three lemmas are the conclusion we are going to obtain. But the proof of the three lemmas are quite similar. It's just those complicated expressions are just algebras. So I'm going to explain the ideas, the rough ideas of how to prove the three lemma, like the common ideas, and I will not prove one by one. So if you want to find the proof, they are lemma 6.4, 5, and 6 in the streamlined proof that I put it on my website. That is joined with Larry Guth and Josh Zahl. So the idea of how to understand so how to understand Planck intersection? I think this is something special about incidences for tubes in R3. So previously, when we want to understand how tubes intersect in R3, we sort of restrict ourselves to just tubes. But one should really visualize tubes and Plancks, they change continuously. For example, Plancks are like is kind of interpolation between tubes and slabs. So recall that in our first lecture, we understand very well how slabs intersect in R3. So basically the L2 argument suffices. And how tube intersect, we don't know yet, but we have some information from the inductive statement. So that is the idea. We want to do some sort of interpolation. So how to do that? We first do some pigeonholing. So assume that this is roughly the same. So the shading on Planck is again a union of A balls. We can, after pigeonholing, we can assume that this is roughly the same for all x, for a typical x. And also we can assume that for a typical pair P1, P2 that intersect x, this means the tangent plane, the planar direction. So if we have a Planck here, let's say this is 1, A, and B, then this determines a planar direction, the two longer side. And this planar direction is defined up to angle difference A over B. So this TP1 is defined up to this. So this is P. And this TP is defined up to angle difference A over B. So we assume that suppose after pigeonholing, the angle between P1 and P2 is roughly theta for a typical pair. Then what do we know? So let me draw a picture. So this part is what uses for the claim in the second claim in the lectures. So let me draw it here. So no matter how they intersect, but suppose the planar direction, it could intersect this way, but it doesn't matter. The planar direction has angle, let's say theta. Then what we know is that we could thicken everything to scale P tilde. So P tilde has side length theta times B. This is B, and this is A. This is 1. So this part we could do pigeonholing such that this holds, and from just this theta, so this is most pairs. So this alone tells us a lot of the information. What can we show? It shows the following. If we take P tilde to be theta B times 1 Planck, that's that's like a thickening of some P, then we know that P tilde, the union of P, intersect P tilde. This should be roughly so this part uses the claim, use slab intersection. why this is true. If we still remember the, suppose we, even if there is, it doesn't matter how the long direction intersect, as long as the tangent plane has the angle about theta, then what we can do is we can look at this b times theta b, like fat slab, and then let's give a name, let's say omega, and let's say P1 and P2. Then P1 intersect omega is, and also P2 intersect omega. They are theta b times b's mini small slabs. Not theta, sorry, A. Yeah. And when theta is 1, then this is like intersecting transversely, right? So by this claims tells us that, so if this happens for a typical point in P1, means that for a typical point in P1, there is a P2 that intersected with angle theta. Our claim in lecture 1, in the end of lecture 1, says that this omega intersect union of P is roughly a. So this is where we use the slab information and like the incidence for slabs, the L2 argument, and this holds for since this holds for a typical point. So for a typical point, there is the corresponding omega here, and that is where we use the slab part. So that is the idea, a brief idea how to prove this part. Are there any questions?
So you're trying to derive lemma 1?
No, I'm not. I'm trying to describe a general strategy of how to understand Planck intersection, and you follow this general strategy, then you can just do some algebra and prove lemma 1, 2, 3, one by one. So yes. The main idea is like Planck intersection is an interpolation between slab intersection and tube intersection. So we are now doing the slab intersection part. Yeah.
I'm a little puzzled, but sorry, it's related to what you wrote.
No, not yet.
Not yet. Okay, so.
Yes.
So I can wait.
No, well, again, I'm trying to describe a general strategy to prove the 1, 2, 3 lemmas using that.
Yeah.
And this is the starting point of the general strategy.
But it's probably a completely silly remark. So I just see that if I make beta equals 0 in the estimate from below on the measure of u of ty that you wrote, I don't get exactly the same thing as in the sticky Kakeya. It seems that there are a measure of t which is missing. Is that correct?
Oh yeah, so the delta square is the measure of t.
But it's almost 0. I mean, if beta equals 0, you don't see the thing. That's the point, you know. I don't see.
Oh, the sticky Kakeya theorem corresponds to the KKT one. I didn't. Yeah, so I didn't put the equivalence there. This is equivalent to union of ty greater than.
Yes, but I don't see it in the last line of equivalence u of ty. Sorry.
The last one is assuming the set of tubes satisfy the Frostman-Wolf axiom, so it's different.
So it's different. So that's why I don't see the.
So, yeah. So the sticky Kakeya theorem, of course, is a like weaker version of this one. Okay. Yeah. So, are there any questions about this statement? I didn't give a proof, but I just try to say that using slab intersection, one could thicken the planks without much loss.
So the theta is A over B, or
no. Theta is in between A, B, and 1. So this tangent plane is defined up to precision A over B, but they could intersect. So as in that picture, they could intersect transversally, or they could intersect with angle theta. That's anywhere between the precision 1. So in other words, we can see that if a typical angle of intersection angle is, so this theta, we call it typical intersection angle. So if the typical intersection angle is large, then we win a lot, because we can thicken the planks without much loss. Means that this thickened plank also has a large density. But what happens when theta is small? Well, if theta is A over B, then they intersect tangentially. This is also good. So it's good for the tube part. So now we are talking about how to use the tube information.
So for what you're saying, so the A over B, if theta is A over B, that's what is saturating your bond, or?
Which bond?
This one, the slab intersection, or what?
Oh no! So when theta is A over B, then this is not this. We are doing nothing, because this P is just 1P.
Okay.
Yeah. So this bond is good when theta is large. And this bond is trivial when theta is A over B. And so now we have a set of, we call those P tilde as a set of thick tubes. We can again pigeonhole in such that for any P in P tilde, the number of planks containing it is roughly n theta. Again, pigeonholing, we can assume everything is even. So for any, we can find a collection of P tilde that covers the original set of planks, and each thick plank contains roughly n theta many original planks. Then, so how do we understand? So this is the first part, and the second part is now we have a set of planks that intersect tangentially. The idea is that, so if they intersect tangentially, then they will rescale two tubes. So let S be theta times 1 times 1 slab. And we define P sub S be the following. The set of P that's containing S, and also their tangent plane has angle difference less than theta. So it means that they should be roughly aligned. So this is our S. This is B, A, and 1 and 1. This has theta. This angle difference is theta. So then P equals to Ts. And we have the follows. Union of Py is greater than sum over S, union of Ps y. And then this is using 1. This is greater than so this P tilde S just means that we take the set of planks here and we thicken it. And then we can define this as y P tilde, which has a large density. Okay, so this is the general strategy. And then what about this last term? We claim that the last term is where we could use those hypotheses, because what's going on is that first we thicken everything to by 1 we can thicken everything to the thick tube that has theta over theta b, and this also is thickened. Sorry, this picture becomes a little messy. But then after anisotropic rescaling, this is mapped to one, and then the thick planks P tilde are going to be B. And this is where we could apply tube intersection. So to understand this term, we use apply tube intersection. And of course, we need to control the maximal density and also the Frostman constant. But that's the basic idea. And then we use the same strategy to prove 1, 2, 3 with some control on the corresponding constant. And for example, for some easy control of those Kastel and Frostman constant, for example, let's just go back to tubes and do some exercise. So this KKT beta implies the following. This is an easy consequence. It implies the following bound. Suppose now we don't know how large is the maximal density of T, then we can like last time, we can always choose T0 inside T. T0 is roughly T divided by the maximal density of T. Then the union of tubes is greater than union of T0 is greater than delta to the eta T0 beta by KK beta. So this if this Frostman constant of T is small, then let's just put 1 here. Then this max of T is roughly the number of tubes times delta square. And plug in this bound, we get the following. We get the union of tubes is greater than delta to the 2 beta plus epsilon, if you want. So this easy consequence is a way of how do we control those. I forgot to say the maximal density of T0 is less than 1. Randomly choose. So using this randomly choose T0, we get some easy consequence of the first statement, and as we can see that this is much weaker than the Kf beta. By this, because when the Frostman constant is small, then the number of tubes will always be larger than, greater or equal than delta to the minus 2. So this delta squared times the number of tubes is always going to be large. And that's why this Kf beta is much stronger than this easy consequence. And this also shows a way of, like, even if our maximal density of T might not be 1, but we could use some randomizing argument to obtain a set with maximal density 1. And this is also like what goes on here, like how do we control those set with maximal density larger than 1. So I will skip all the details, but that it's like randomizing argument, randomly choose a subset argument, and this general strategy of how to understand intersection of Planks. So now let's start the proof of. Now we can start the proof of main lemma 1. Proof. Before I move on, are there any questions? I know I'm going a little too fast, but again, this part is also somewhat self-contained. It's not the most difficult part of the argument. So I went through it quickly, and you can check those short lemmas, rather short proofs of the lemmas in the paper. Okay. So I'm going to state a main lemma 1 prime. I think suppose KKT beta and KF gamma holds for some gamma minus beta, gamma greater than beta. Then we can find some new positive that this holds for a smaller gamma. So as you can see, that it suffices to prove main lemma 1 prime. And how do we do it? So fortunately, we still have the sticky Kakeya theorem here. So we are going to choose a beta target that's between 0 and beta, small. And because we are going to have many small parameters, so I will give them names to easier to remember, and let epsilon sticky be this exponent. Okay, so maybe it's this. So this epsilon sticky is plays a row of eta here, be the exponent such that for any t is delta to the epsilon sticky, and density is greater than we have a union of tubes greater than beta target. So the beta target plays a role of epsilon, and then this epsilon sticky plays a role of eta. The reason is because there are also epsilon eta over there, so we have to use some other names. And also this choice of names tells us that once the sticky Kakeya theorem is proved, and for those exponents, we should view them as large, because the epsilons and eta over there are going to be much smaller than the ones here. And maybe there will be many small parameters. Let me just use this place to list them and talk about their relations. So we are going to choose an epsilon scale that is much smaller than gamma minus beta epsilon sticky. And this is much smaller than, much larger than eta j. And then j is going to be 1 over epsilon sticky and epsilon scale. And eta 1 and much smaller than eta. Where is our nu? The improvement nu is somewhere here. Okay. Okay. So we are going to use some kind of multiscale stopping time algorithm to okay. So let me just say that what is the general strategy? So to prove main lemma 1, we first face a set of tubes satisfies the Frossman-Wolf axioms. Means that we have a lot of tubes, and we're going to use multiscale decomposition or stopping time algorithm to find either a sticky set or a very non-sticky set. For the sticky sets, we could apply the sticky Kakeya theorem, and for the very non-sticky sets, we are going to use this factoring proposition that we proved last time, that together with lemma 1, 2, 3, that controls how the W's intersect to reduce to this case or improvement. So our goal is to show that this holds. Yeah. So this just says that we have some new improvement. Maybe this new is not exactly this new, but like some 0.1 new, something like that. Okay, so the first step is check if there exists rho between 1 minus epsilon scale and delta to the epsilon scale, so that the Frossman constant inside T rho is small. So here, this is for one T row, but when I say check if this holds, what we are doing is that if this holds for a significant fraction of T row. If no, we stop. So this is a very non-sticky set. So this means that T is very non-sticky. The goal is to say that either we find a sticky set or we find a very non-sticky set. And otherwise, define T1 to be the set of T row and T2 to be T. This means a rescaling of the two delta over row tubes. So this means that we could, if the Frostman constant here is small, then this, in some sense, we could break the tubes into two scales without much loss. And here we mean that T row, it means that the set of T row such that this holds. And also, again, this is, yeah. So that's the beginning of this stopping time algorithm. Are there any questions? So we get the following. For j equals to 2. Sorry, I should add the name j max here. That's the maximal possible j. For any j from 1 to j, Tj is a set of delta j tubes. And second, the product is delta, and then the size product to T. And so here we assume that our T is uniform and all the nice pigeonholing, we have done it before. And also we have the following. The Frostman constant of Tj is less than delta j to the minus. So it's bounded by the smaller one. And number 5, we have mu t is less than j equals 1. Okay, so here we need to choose this eta is going to be very small anyway, so we can choose it to be less than eta 1 times epsilon scale. So that okay. Yeah. So far, suppose the Frostman constant of the thin tubes inside the thick tube is small, then we have the following 5 items. And we are going to keep repeating this algorithm to find those holes. Either we find a very non-sticky set, that's the opposite of that criteria, and or we could just keep going. Are there any questions? Okay. So the general step is the follows. Suppose for some j we have the set of tj's obeying 1 through 5, then we can check if there exists j and a scale rho such that a delta j is less than delta to the epsilon sticky, b rho is between scale and c the Frostman constant is less than the corresponding so what are we doing here? So the idea is that let's say this is delta, this is 1, and we know that the set of tubes has small Frostman constant, and if this is small, then it automatically implies that let's say so the Frostman constant, if the set of tubes are uniform, then the Frostman constant of the thick tubes are automatically bounded by the Frostman constant of the set, and then of the set of tubes. So this part is good if this is rho, and then the criterion of Frostman constant inside T rho is good, just says that if we break it, then this part is also good. So in other words, if it's we also have this multiplicity bound, so this means that we can successfully decompose our set into 2 scales, where each of the scale we could apply the Frostman the KF gamma, for example. Okay. Now let's imagine the following scenario. What if we could keep breaking things? So if we can if we can factor at this rho, then if we could keep factoring, and such that this adjacent scales has difference less than epsilon sticky, and if we can keep breaking, then this means that the set will contain a sticky Kakeya set, and we are done. So the goal is to say that either we can keep breaking it, or we stop and we find some intermediate scale that has a very non-sticky set. So this criteria is to check that the intermediate scale, the scale difference is still less than that, because if it's greater than that, then we are happy. We don't have to break it anymore. So the scale difference is less than that. And this just means that to check what's going on is, let me try to explain. So this is 1 and this is delta. So we have some rho. We first check if this guy has a scale difference less than this or not. If it's less than the sticky scale, then we can ignore it and then focus on the rest. And if, sorry, not less, if the scale difference is bigger than the gap is bigger than the sticky scale, then we could ignore this part. So it should be like this. If rho is here, then we could ignore this part and keep breaking this part. But if the gap is larger than the, yeah, it's kind of, if the gap is not the gap, the scale difference is more than the not more than, how do I say? If this scale is less than this sticky, epsilon to sticky, okay, just means that if the interval is large enough, and then we can we want to keep breaking, and the way we break it is the same way as step 1. That is what I'm saying. Yeah. So if no such J and rho, then we stop. Otherwise, replace Tj by Tj rho and Tj T rho and relabel tubes, sets of tubes to be T1, to be T1 and Tj plus 1, because we have split Tj into 2 sets. So which this obeys 1 through 5. Okay. Yeah, so that is the stopping time algorithm. And how do we know that it has to stop? Sorry? Oh, there's another one. Okay, good. How do we know it's a little far away? How do we know it has to stop? Since this is less than delta to the epsilon sticky and epsilon scale. Why this is the case? The reason is that previously the scale we decided to break should be less than delta to the epsilon sticky, and then when we break it for the rho. So let me just say this. Let's say this is delta J. Okay, it's. Let's say we decide that this interval, this scale difference is less than delta to the epsilon. Delta J is here, less than delta to the epsilon sticky. Suppose this is the scale we decide to break, which is we can break, that is less than that. And then the way we break it is we find a row that is between delta j to the 1 minus epsilon scale and delta to the epsilon scale. So rho happens here, in some sense. Like a rescaling of rho happens here. So this means that the corresponding, if we obtain the next level of delta j prime, then this scale difference should be less than delta to the epsilon sticky times epsilon scale. And that is why we know that the resulting delta j is always smaller than delta to the epsilon sticky times epsilon scale. So which means that when we keep breaking those intervals, the smallest the interval, which is the largest scale difference, has to be less than that. So this implies that the maximal number of the intervals is 1 over epsilon sticky times epsilon scale. So this means that we have to stop. Implies that stop before and j is less than j max. So we split into 2 cases. So now we have stopped, and then we are going to analyze them depending on the information about Tj. So we split into 2 cases, sticky case, which means that so the sticky case means that every delta j is greater or equal than delta to the epsilon sticky. It means that when we are doing this general step, the reason we stop is because item A does not hold. So the sticky case is if every delta j is greater than that, then by the same random choice argument, so that's section 7, T contains a sticky set T prime with so this at least that's a delta to the epsilon sticky set. And then we can apply this sticky Kakeya theorem to conclude. Okay, so I'm skipping a lot of details, but that's the case. So if very non-sticky case, so I guess this algorithm is to say that in general, when we look at the sticky Kakeya theorem, we sort of say that okay, the opposite case of being sticky is there exists a rho such that the maximal density of T rho is large, but after this algorithm, in fact, the opposite of sticky case is that there will be some Tj such that the maximal density is large for all. Eventually, we will prove the maximum density is large for all rho. Okay. So the very non-sticky case is as follows: for at least one j, we have both. This is delta j is less than delta sticky, and Tj is very non-sticky, which means the follows. Just I'm copying. Okay. This first step here it means that the opposite of that means that for any row between delta j 1 minus epsilon scale and delta j epsilon scale, the Frossman constant is greater than delta j over rho to the minus eta j. So notice that this is eta j, capital J instead of eta small j, because we only look at the what stops at the last step. So we have this eta capital J. This is important because we choose this eta capital J to be a lot larger than all previous eta small j's. So the idea is that again we can decompose it into many scales, and suppose there is one scale that is very non-sticky. Let's say it's this scale in the middle that is very non-sticky, and what are we going to do is that it's very non-sticky by a lot because it's by eta capital J, eta sub capital J, and the rest we can break it with at the cost of something to the minus eta j minus 1. That is the reason we need to choose this guy to be much smaller than much smaller than eta capital J. So we will eventually have some gain here depending on the size of eta capital J, and then all of here we will have some loss, and the gain here will absorb the loss. And I'm going to make this precise. So recall that mu t is less than product of mu t j y. Okay, let me use the k here. And for the not equal to j, and then for each of this, we could apply a consequence of Frossman kf gamma. So we can apply this, and so it suffices to show mu t j y is less than, let's say, 10 eta j minus 1, and then what predicted notice that here it is those things are delta j, and this is delta, but it is okay if we choose, let's say, eta j minus 1 to be less than eta j times, let's say, epsilon sticky, and epsilon scale, and even to some power, something like that. Because these are going to be chosen, and then scale is also going to be chosen. Those things are relatively large, so and then we can choose a sequence of the small things. Yeah. So this is what we can. Okay, now how are we going to do it? We are going to apply this factoring proposition. Maybe before I move on to study that using the property of being very non-sticky, are there any questions? And this is the property of very non-sticky using this. Okay. Here is what we are going to do. Pick sigma equals to delta j to the 1/2, and then we know that the Frostman constant is greater than and apply factoring to so since the Frostman constant is great, it's large, we want to know why it is large. And to do so, we just apply the factoring proposition to and obtain that this WT sigma to be the maximum factoring a set. This is a set of A times B times 1 Planks boxes, where we have the following delta. So delta J is less or equal than A, less equal than B, less equal than sigma, less equal than 1. Because everything is contained into sigma. And what do we know from the factoring proposition? We also know the following. The Frostman constant of Tj, W, is small, and the maximal density of WT sigma is also small. So that's the two most important consequences of the factoring proposition. And now we are going to do case by case. Oh, I don't know that it goes up.
Sorry, you want it down?
No, it's fine. I don't know that it can go up. Okay, now it's much better. Yeah, now I know why you said there is a third one. Okay, good. Okay. So we're going to split into, again, as we said, we are going to split into cases depending on the size of A and B with respect to delta J and sigma. So what do we? So before that, let's first do the following. So if So if A is close to B, then we know that W's are essentially roughly a tube. Then we have some control on the density of Tj in Tb. That is okay, notice that this is A is smaller than B, so I'm just saying that when A is close to B, then they are like tubes, so the density should be roughly the same. And then this implies that the Frostman constant of Tj Tb is less than B over A. Yes. So because we know that this W inside it has a large Frostman, has a small Frostman constant, and then how different is W compared to Tb is like this different. So we have some control on the Frostman constant. And now, how are we going to split into cases? Recall that if B is greater than, since B is already less than like delta J to the 1/2, if B is greater than 1 minus epsilon scale, then this very non-sticky assumption, the one in the yellow box, tells you that if B is greater than that, then B can be the candidate for a row. Then this says that then the very non-sticky case assumption says that the Frostman constant of this should be greater than delta J over B to the minus eta J, which is greater than delta J to the minus eta J over 2. And this means that if B is greater than this number, then it implies that B over A is should be greater or equal than delta J to the minus eta J over 2, because like this number is greater than this number should be greater than that number. So we have either this fails, so it means B is less or equal than, or we have B over A is greater or equal than so the first case we call it small case, and this case we call it eccentric case. So we are going to split into two cases. For for the eccentric case, we're going to use the gain on this lemmas here. Maybe let me. Okay. So, eccentric case. We are going to use the lemmas to estimate the intersection of W's. Let W be the union of WT sigma. Then we have the following. I'm ignoring the shadings. And where, okay, let me just tell you the shading is a neighborhood of the union of so since we know that by the two-dimensional Kakeya, since the Frostman constant is bounded by 1, and once we have thickened the TJ to tubes of radius A, then it becomes like a two-dimensional problem in W, because W is A times B times 1. So this just means that the shading on W is well defined, and it's still quite dense. And so we are going to use this lemma 3 to estimate both terms. So we are going to use lemma 3 to estimate the first and the second. Let's try to read lemma 3, although I didn't explain what that is. This lemma 3 says the follows. This P tilde are the thick planks. And in most cases, we could ignore the Frostman constant. It will be small anyway. And then, so when we look at the multiplicity, we see this term. And this is where what can give us some gain, because A is smaller than B. That is where we use the eccentricity. And also, for some cases, for example, W, because this W has, it's like, this W has maximal density of WT sigma is small. So let's look at this picture. So we have a lot of T sigmas, and these W's are contained in sigma. And we know that the maximal density of W's in T sigma is small. Then this implies that this n theta will be small for our W, so this will also give us some improvement. Okay. Oh, but I need to put this up. So first we estimate the multiplicity of W. Now we have a Kf gamma. So every beta here should be replaced by gamma. And then we have a lot of those terms. We use this one. And then what is let theta be a typical intersection angle. Then we claim that n theta is always, for any theta, is always less or equal than theta times b over a, since the maximal density is less than 1. So why is this the case? So recall, so we have T sigma, and the W is here. And we want to estimate, so this n theta is when we thicken this W to n theta, so to theta b times 1 Planck. So all the relevant W's contained in this blue thick ones, so this is W tilde. All the relevant W's contained in this one is also contained in the corresponding T sigma. So we only need to use the maximal density of W T sigma. And so using that, we can control the number of W T sigma contained in W tilde, which is less than the volume of W tilde divided by the volume of W, and that is theta b over a. So this is a. And also we have the Frostman constant of W, let's say in B1, is less than the Frostman constant of Tj, less than. So why is this true? Because in the factoring proposition, we make sure that any W contains about the same number of Tj. So we're factoring, yes, because every W contains about the same number of Tj, so we have this bound on the Frostman constant. Then we have, so this term is going to be small, and we also know this term, so that is how we could plug in. So this is less than a to the minus epsilon. Since this is for any epsilon, the following holds. So we could just use epsilon over 2 instead of epsilon. Then theta b over a, gamma over 2, a over b, b to the minus 2 gamma, and b squared W 1 minus. And then this will introduce an error of size delta j to the minus. It doesn't matter which constant I put here, it's going to be absorbed anyway. Okay. So since here this is positive on theta, and so the worst theta is 1, so I can just remove that. And then this is a b to the 1 minus gamma over 2. Okay. Now we do this this gives us the mu W term. Now we want to estimate this mu Tj W. So how do we do it? Let me just draw a picture. So suppose this is our W, which is this is B, A1, and we have a tube contained in it. This tube has a radius delta J. And this, after rescaling, becomes this tube becomes Planck. So this is delta J over A, and this is delta J over B, and this is 1. And we are going to apply lemma 3 to this picture, to the rescaled picture. So we need to understand how large is theta n. So n theta, so how many, let's say this is theta delta J over A. We want to understand how many yellow planks are there contained in the blue plank. But this blue plank, after going back, is just another flat blue plank. We want to understand how many tubes are there contained in this two-dimensional small plank. So this tells us that this picture, so what is the width? The width is theta B over A times delta J. And this tells us that n theta is less than theta B over A square. So notice that this is worse than this one because for previous one we have a very nice maximal density control, and here we don't have any. So this is the worst possible case, but it's still okay. Here we are using the fact that the number of all distinct tubes contained in this blue plank is bounded by this number. So this says that it is less than delta J over B to the minus epsilon over 2 A over B 1 minus gamma. So this is gamma instead of gamma over 2 just because there is a square here. And then delta J over A minus 2 gamma. And then we multiply them together. Mu Tj is less than the product of the two. So this gives us delta J to the minus epsilon minus 2 eta J minus 1, delta J to the minus 2 gamma, A, B, 3 gamma over 2, delta J squared. And this is because Tj is roughly Tjw times the number of W's. So this is where we use eccentricity. Since A over B is smaller than delta J to the eta J over 2, we obtain a gain because we choose eta capital J to be much greater than this number. So we are going to choose delta J to the minus. So and also we know that this is less than. So we choose this to be large, and then that's it. Yeah. So we are done by choosing much larger than. Okay. Good. So this is so this is the very eccentric case. For the small case, let me just say a word, and we should stop. Small case. So for the small case, we know the follows. We know that delta j is less or equal than b, less equal than delta j to the 1 minus epsilon scale, that is small scale. We know that w is almost a delta j tube. So this means that we also know that the maximum density is less than the maximal density of W's. So we apply this KKT beta instead to TJ. So because this beta is smaller than that, than gamma, we win. So the small case is like a tube case, and this is how that's the proof of the main lemma 1. And we'll take a break here. Okay, so now for the last part, so let's prove main lemma 2. We can, using the same reduction, that's what we have been talking about, we could, let's say the main lemma 2, each time we prove a prime, so now we need to prove the main lemma 2 prime. I think that is the very non-sticky case of main lemma 2. That is for follows. For any beta greater than 0, suppose there exists epsilon scale okay, the assumption is for any beta greater than 0, there exists epsilon scale, so that for all zeta greater than 0, there exists nu depending the improvement and eta, so that the following holds. So suppose KKT beta and KF beta and T is a set of delta tubes contained in a unit ball, obeying the following. One is the maximal density of tubes is less than delta to the minus eta. 2 is for any row between delta to the 1 minus epsilon scale and delta to the epsilon scale. We have a lot of tubes. Then the multiplicity, we have some improvement on the multiplicity bound. So if we don't have this assumption, then in some sense this is the main lemma 2. This additional assumption is very non-sticky, very similar to very non-sticky. And the reduction of main lemma, I should say, if we know how to prove this lemma, then how do we show the main lemma 2? This is essentially repeating what we have done so far, the same argument. So the ideas are very similar, but it still takes many pages, like a few, maybe 5 or 6 pages enough. So I will skip it, and then this is the section 9.1. So for the rest, we are going to prove this very non-sticky case of main lemma 2. So to start the proof, so let rho be the very small scale, that is delta to the 1 minus epsilon scale. And then R1 is just delta over rho 1 equals to delta to the epsilon scale. So R1 is very big. And then we use that decomposition, like when tubes have angle about rho, they intersect into very long segments. And this, we start with a very long segment, and that is why we need this it's useful to have this very non-sticky assumption. We start with a very long grain, the red one, and then we are going to apply the factoring proposition to the set of grains. As we discussed, that's our main strategy. Now we obtain a set of W's, A times B times R1 W's. So let me first say things in words. So we decompose union of R1. Okay. So the B's are both of radius R1. And then we give them a name, right, TB to be the set of grains delta times R1 grains. Previously, I called them G, but since I will need to discuss what happens in different balls, so let me say that this is a B, and this is TB. So here we apply, we essentially apply the factoring proposition, but we need to apply a modified version of factoring proposition to T sub B, and obtain corresponding W sub B, that is A times B times R1 boxes. Delta with A with B. And then let tau be a small parameter. Okay, I should say that the proof of main lemma 2 is the main part of the main argument of proof, and it consists of many parameters and cases. So here are the yellow boxes are the constraints on the parameters. So it's a nice exercise to see that actually we could find the parameters that satisfy those constraints. And let me just briefly explain what are the names mean. So we apply on those this fraction proposition to obtain those W's, and then the W's we are going to discuss split into cases similar as before, but now there are more cases. The thick case is that when A is large, greater than delta to the 1 minus tau, in which case we would expect, since it satisfies the Frossman-Wolf axioms inside W, we expect the W's to be to contain a lot of tubes, and so it should be quite dense. And then the thin case means that the W's, the A is roughly the same as delta, and the thin case are split into slab case, in which case this W is like a slab, so it means that B is quite large. And here we could use this L2 argument. And there is a not slab case when B is small. Then we also split into cases according to how those W's intersect, because since now W is very thin, so we know there are a lot of tubes contained in W, and this is essentially a two-dimensional problem to conclude that the W's are essentially filled out by those grains. And then we use if it's transverse, then again by this claim we had before, the same argument, we know that locally it fills out a ball, a thick ball, and so we could do some thickening argument. And if they intersect tangentially, then as before we have a way to understand tangential case. We just organize them into big slabs and rescale to tubes. So these are all the cases we have to deal with, and the yellow boxes are all the constraints that comes with it. Yeah, so that's the general strategy. Before I move on to calculations, are there any questions? Okay. So here are the details. When we do the thick case, our goal is to show that the union of tubes is greater than, so yeah, because this is just a translation of this goal by double counting. It suffices to show that the union of tubes has volume greater than what we previously had before. Before that, when I say here that it fills out some thick ball and we could apply some thickening argument, what does it mean precisely? I'm going to describe what we mean. So this is, again, is a general thickening argument. So let delta between R and 1. So this R could be anything. For example, R could be the A there. Then what we can do is, after refinement of shading, we could make the following happen. So this is by pigeonholing. After refining to some Y prime, which is the union of R tubes times BR intersecting and this BR is just anything inside the union of R tubes. So we have this bound, and again, after pigeonholing, we can assume that for each ball of radius R contained in the union of R tubes, this quantity is roughly the same. So I don't need to talk about the soup. Yeah. So this is the thickening argument. Roughly speaking, if we know that this quantity is large, and then we will apply some induction. Okay. So how do we estimate T union of R tubes using KKT beta? Here we use the easy consequence of this KKT beta we have calculated at the beginning of today's lecture. So first of all, the maximal density of TR is less than the maximal density of T on R delta square, R over delta square divided by, and then I'm just going to repeat the argument, choose TR prime in TR with probability 1 over the maximal density. Then we have the maximum of TR prime is less than 1. So we could apply the KKT beta. Union of TRY is greater or equal than union of TR prime Y greater than R to the epsilon prime 1 minus beta R squared. And this is greater than delta squared So the reason is that if we calculate this number, then TR prime is number of tubes TR divided by this number. So this gives us number of tubes divided that is where we have this term. Okay. So it means that it suffices to show the following, and then we plug in that formula suffices to show there exists some R such that the local density is large. And how large is enough? So that is our, this is what is enough for the thickening argument. So if we can show that for a typical, there exists some radius, and for a typical ball of radius R, the density is greater than this number, then we are done. And this is going to be used both in the thick case and also in the transversal case. Okay. And but to obtain the improvement in the thick case, we need to modify the factoring proposition a little bit. That's why we have this parameter eta factor. How do we modify it? So we choose, during the process, we're going to choose W to maximize. W to the minus eta factor. So in the abstract world, this is V, but in application, it's just TB. So I'm going to write here. So what has changed? In the previous proof, when we prove the factoring proposition, we choose W to maximize just the density. And here we give us a little room so that we can make sure that there are this factor many more tubes inside a W. So here are some consequences. So this is the only change in the process. So the consequence. Again, this holds for general V, but I write TB here because we are applying it to B. This TB prime is a refinement, but this is greater than TB to the eta factor. Plus 1. So it means that it has this more tubes than what we previously want. And also, the second is the delta max of W. So I think I used the word W sub B here to be the factoring, the collections of W's that come out is less than B over W. Okay. So the consequences are, first, there are more tube segments contained in each W. And the second, so this is good. And this is something that's bad, that's slightly worse than before. That is, the maximal density previously is bounded by 1. Now it's no longer bounded by 1. But by our choice, this will eventually be since this eta factor, we are going to choose it to be not so big. This will eventually be absorbed. This will be overcome by the eta. That's zeta. Yeah, zeta in the statement of the very non-sticky case. So this will absorbed by the fact that T rho is greater than rho to the minus 2 minus zeta. So this will not. Okay, so this is we need to apply the modified factoring proposition to TB. And this is what we obtain. Yes, I should also say that the proof of this very non-sticky case of main lemma 2 is somewhat independent from the previous, the proof of main lemma 1. So if you are lost for that part, you can come back. So, okay. So what we are going to do is we want to estimate the density of so we want to in other words we want to estimate the union of tube segments in W, and then this will give us a density of BA intersect union of tubes. So that's the goal. Because A is relatively big, so we want to show that this is this big. And how do we do it? Now the picture is that we have done such kind of argument before, but let me just repeat it. So this W is a set of now A times B times 1 plank, and those are the delta tubes. Then we rescale. So the goal is to apply, apply lemma 3, and so we are going to apply lemma 3 to estimate this term, and we are going to rescale it to 1, 1, 1. This is not 1, this is R1. This is our TB, and this is our W. And now, once we rescale it, this TB becomes a plank. So let me just write here. The goal is to apply lemma 3 to estimate this term. So we need to understand what are those terms. Like, since we want to have a volume bound, we want to understand how large is the thick planks. And then let's say theta is the typical intersection angle. So this part is delta over A. And then this is delta over B. This yellow thing is the thick plank P. This red thing is the plank P. And sorry, I'm wrong. The thickness here is delta over B. The width is delta over A. And then the thickened one is delta over A times theta. So let theta be a typical intersection angle. And then we rescale back. This is again a flat plank. Let me call this a TB tilde to denote to just correspond to this name P tilde. So the P tilde rescale back to TB tilde. And this width is delta B over A times theta. Okay, and just to draw this picture, so our goal is to show that a typical ball of radius A is large. Okay. So it suffices to show P tilde times P is greater than delta to the minus and which is the following. This equals to TB tilde Okay, maybe before I do that, just so this equals to W times the union of P, that is greater than the volume of W times delta over B to the epsilon over 2, delta over A to beta, and then beta over 2. So the density, this, yeah. So this yellow box, the density is going to be this one, because we want to understand like the union of tube segments in W divided by the volume of W, then it will be the average density of a ball of radius A. So we just want this term to be nice, and as with A in place of R, and we already see that this term they agree, so we just want this term to be big. So need to show that this is bigger than delta to the, let's say, 4 nu plus eta over beta. Sure. And each of this term, the P tilde will be the number of the number of T tilde B, which is this one, contained in W. And this one is TB tilde divided by the volume of W, because it's rescaled back. So we just want this term to be greater than this number. Want to show. Okay, how is this the case? This comes from our modified factoring proposition. Because the density of TB in in this plank is less than so why is this true? Because we choose W to maximize that number. So it means that this T tilde B does not maximize the number with T tilde B in place of W. So just translating the criteria of the W gives us this quantity. And then we calculate this equals to TB W divided by, since everything has approximately the same number, times yeah. So this is equals to the density of B, the density of TB in, and this is greater than the volume of W divided by the volume of B tilde to the eta factor. And this is where we use A is much bigger than delta, because this number is greater than delta over A. Since TB has thickness delta and W has thickness A, so it is at least maybe I should just put A over delta here, eta factor. And this is greater than delta to the minus eta factor tau. So this is where we win. We have this greater than that, and it's greater than this. So we want this number to be greater than this number, and that is where the thick case, yeah, over beta. Yes, so eta factor tau is greater or equal than 4 nu plus eta over beta. And that is the criteria in the thick case. And this finished the thick case. Okay, we have half an hour and 2 pages to go. 1.5 pages to go. I think I'm good in time. Okay, so yeah, this is the calculation for the thick case. It's this is also the reason why we need the main lemma 1, because this really shows that we need to have this gain when we have a lot of tubes. So we have when our planks, the number of planks is more than expected, then we need to have this gain. So this is where we need something positive here, rather than the easy consequence of KKT beta, where this all vanishes. Yeah, I think this thick case is the reason why we have to go through the main lemma 1. Okay, now let's do the thin case.
You want to put down?
Kakeya.
Which one to you? This one you want?
Yeah.
This one?
I'm still thinking. I I think I still need the. Let me use the middle one first. Yeah, let me just put this one on the corner that we are going to use later. So this is what we need for the transversal case. Modify factoring. We have. Let me first start the thin case here. Okay. B thin case. So the slab case is not very hard. Maybe I could just say it in words. Slab case. Okay, maybe before doing that, the thin case tells us the follows. So the 2D Kakeya, because it's very thin, it says that the union of TBW is going to be greater than delta over, let me just put O tau plus eta here. What's more than that is if we define the shading on WYW as the A neighborhood of union then we know more than that. We know that YW, I think maybe I explained it before, is greater than delta to the 2 eta W. So this means that the density is still very large when we. This is still very large when we because eta is the smallest possible parameter. So the slab case, we apply Cordoba to just show that since we know the maximal density of T is less than delta to the minus eta, this implies that the maximal density of TB in W is still less than minus scale. The reason is that TB is not that far away from the tubes because it has a large length. The length is delta to the epsilon scale. So we have that. And this implies that we also know the following. We also know the Frostman constant is small from, I think from the maximal factoring. Yeah. And the Frostman constant is still less than 1. Yeah. So we know that is small. Again, I should have replaced TB by TB, blackboard TB prime, but I'm ignoring the primes, the refinements. So this is less than 1. This implies that it is both Frostman and roughly Katz-Tau. So this implies that we know pretty well the cardinality. So And in particular, this shows that the maximal density of W is less than because each W contains this many TB. So using the slab incidence, this shows that the multiplicity is small, so the union of W's so using slab incidences, we calculate the union of W's to be delta to the epsilon scale, and then number of W times the volume of W. And I should also add this term. So let me as you can see, this comes here, and then the loss of delta to the epsilon scale coming from estimating the union of W's. This just is greater than So in the slab case, we have very good estimate. We have almost sharp estimate. And if you do some algebra, this tells you that you need nu to be less than this number. Because we are choosing our epsilon scale to be much larger than the rest of the parameters anyway. Okay, so that is the slab case. Okay. Maybe. Yeah. Okay. Let me do the transversal case. That is when theta is, the typical intersection angle is large, when theta is larger than delta to the minus tau prime, A over B. So A over B is the smallest possible. That's the how the tangent plane is defined up to an error of A over B. And then we choose another number, tau prime, that's bigger than tau, to say that, and then transversal case when theta is greater than this number. So now we can in the transversal case, we have the follows. Using the same using the same Planck analysis, so this is a consequence of what? This is a consequence of when we take this W tilde to be theta B times B times B, Previously, we showed that union of W's intersect W tilde is still so this 4 is not important, but this is what we showed previously when we used the Planck thickening, and then on average, this gives us this number. And now, since W is in the thin case, we know that W is also full of tube segments. So this implies that it's greater than delta to the tau plus eta d, and if we take, so the reason is that if tau prime is sufficiently small, the reason is that theta is big. So this term is relatively small, so we can, like, this dominates this term with an additional factor of delta to the minus nu. So this is where we have the criteria for the transversal case. That's where we want this tau prime. We want this tau prime to theta to be large, and we are done. And so once we have that, we obtain that thickening argument, what we need for the thickening argument. So this is the transversal case. And finally, our last step, we are at the tangential case, and we need to do some non-trivial calculations again. And we have 20 minutes to do so. Tangential case. This calculation is quite similar to before. So the tangential case is theta is less than minus tau prime A over B. For this part, I think, and also recall that it's in the thin case. So A is again from delta to delta 1 minus tau prime, 1 minus tau. So what it means is that we could pretend theta times B to be roughly delta up to a factor of tau prime. And just for simplicity, let's just pretend this is delta. So what are we going to do is let I think I didn't draw the tangential picture. Let's just write it delta, and then B times 1. And we let, not B times 1, this is R1. So we let this angle be rho 1, or rho 2. Let rho 2 equals to B over R1. And we have the following: mu t is less than mu t rho 2 y and mu w y. Why this is true? Usually we would put t rho 2 here, but since rho 2 is significantly bigger than w, so this is w, and then this is rho 2. So all the thin tubes that intersect this w tangentially will always be contained in some rho 2 tubes. So that is why we have this decomposition. And let's just add some delta to the minus O tau prime factor to fix this possibility that it might be like tau prime away from delta. So we have two terms. Let's say this is the second term, and this is the first term. So it means that the delta tube. So we could use multiplicity of W instead of multiplicity of rho 2 is because each thin tubes they intersect and they will be covered by some W, so we will, like this term is dominant. Maybe before I move on, are there any questions about this decomposition? Okay. Yeah. So again, this is like somewhat it's somewhat better than the using T rho 2 here, because this W is like sitting sort of like a grain. In fact, those W's are the original set of grains when people talk about grain decomposition, because the thin tubes in T rho 2, when they intersect, their intersection is contained in some W. So how do we estimate this multiplicity of W? We do as before. Since we know that W's intersect tangentially, we are going to cover it by boxes. So let S be theta R1 times R1 times R1 slab. Again, theta is the typical intersection angle of W. Then we write W sub S as the collection of W's contained in S and their tangent plane has angle difference less than theta. And also we know that theta is relatively small, so I could avoid using that. So mu Wy is less than sup of S mu, and then we do change of variables. We convert S to ball of radius 1, and this is basically the same picture as before. So let me just draw it here. When they intersect tangentially, and this is our S. this becomes unit cube, and the W's becomes row 2 tube. So I call them T tilde. And WS becomes T tilde, which are row 2 tubes. And the maximal density of WS is less than the maximal density of W's, which is less than delta to the minus eta factor. Well, the eta, this comes from the second bad term here. That's what we said, that for the bad term we have some eta factor, but it's fine. So this is less than mu T tilde is less than so now we apply K, so to estimate this term, because it becomes a set of tubes, so we can and also with maximal density relatively small, so we could apply KKT beta. Here we need to be a little careful. That's probably fine. We apply this KT beta, so this is less than rho 2 to the minus epsilon T tilde beta. Okay, here is where we use the that zeta over there, because we know that this maximal density of T tilde is small. So we know that this implies the number of T tilde is less than rho 2 to the minus 2. However, we know that the number of rho 2 is large because of that very non-sticky hypothesis. So this altogether gives us delta to the minus eta factor. And then rho 2 to the beta zeta, the number of T rho 2 beta. So this is the crucial gain that we have from the very non-sticky case. Just because T rho 2 has very large cardinality. Yeah, so the second term is just by induction, and this is bounded by delta to the minus epsilon. Okay, delta over rho 2 to the minus epsilon times T rho 2 to the beta. So we multiply them together. We have this term together with this term give us T to the beta, which is expected, and then we are left with this term. So all we need is to show that this is the gain. It's much better than this guy, and that is why for the tangential case, we need the following. In fact, this one I don't think we need it. So that is where we need the second term. Yeah, and here, I think this is this is all the argument. Yeah. Okay.
Okay.
Yeah. Okay. I think some people told me that I just maybe use 5 minutes to say that maybe the connection to restriction.
Yeah. Yes.
Yeah.
Yes. Sure.
Yes. Some people ask me about restriction. So restriction is related to the Kakeya problem via the wave packet decomposition. So we have, so if we want to estimate Schrödinger wave, then we will see the waves supported on those long skinny tubes. How does once we know, we have some idea of how tube incidences in R3, how do we understand how the wave packets interact in R3? So the main difference between this and the Kakeya problem is that here we see that there are some parts where a lot of waves intersect, for example, this part. And there are some parts there's no other wave intersect. So we expect those on this part the function should be small, and so those yellow points where there are a lot of tubes intersect are the main enemy point. So this is the difference between one of the difference between restriction and Kakeya is that the density of the shading, so YT is a subset C, could be small. So to understand the restriction conjecture, we need to understand the geometry for union of shading for all kind of shadings. And this is related to something called the Furstenberg set conjecture, let's say in R3. And in a joint paper with Shupeng Wu, we studied how the Furstenberg set conjecture is related to the restriction conjecture. And I should also just add one disclaimer. So with Shupeng Wu, I think we put it online last year. In that paper, we had 2 ends of Furstenberg set conjecture, which we proved in 2 dimensions, but it turns out that it is false in higher dimensions. It was disproved by Alice Cohn. But the point of that 2 ends Furstenberg set conjecture is that if it were true, it would imply the restriction conjecture. It's purely geometric. It's just about union of those shadings. But unfortunately, it's not true. However, there is another more standard called Furstenberg set conjecture. Might still be true, and I would hope that the techniques here would help in studying this conjecture, which in turn might help understand at least some parts of the restriction conjecture. I will stop here. Thank you.
Thank you.
Questions, remarks? Yes, so I want to go back to my original question on dimension 4. So already to prove, if you apply the Wolf argument, I guess you improve the bound. If you know that the dimension 3 is good, then you improve or not the bound in dimension 4?
Apply Wolf's argument.
Yes.
But Wolf's argument is about finding a popular tube and then consider all the other tubes that intersect it.
Okay.
And then I think that's a good question. I've never thought about it.
Okay, okay. The following question: you thought about your proof. So using your type of argument, can you improve the bound in dimension 4?
I think what you propose is a very nice idea.
Okay.
But that I should check the numerology. But you mean what? Well, I guess what you mean is like what goes wrong for.
Yes, especially the sticky case. Do you have the sticky case in dimension 4?
Yeah, we have some idea.
You have some idea.
But the general case, it's this like this rescaling argument will not work. Because this W. Previously we said those are the W's, but for dimension 4 the W's are semi-algebraic sets.
Okay.
And then we cannot really rescale to tubes.
Okay.
It's more complicated.
Okay.
Yeah, that's one of the main difficulties for.
Okay.
But also maybe for people, can you just, you spoke very fast and people are not well aware about this restriction theorem in dimension 3. Can you just say what is it?
Yes.
But people which are less familiar with this problem.
Yeah. I'm sorry. I'm going through it very quickly. So let's say F is from R2 to C, and then extension operator. So X is in R3. And then, so it's Stein's restriction conjecture in R3. Says that the LP norm. Let me just put the n-1 here, and n2 n over n-1. Rn is bounded by a constant only depending on p and n times the LP norm of f. I think here we want to. This conjecture, if true, would in any dimension n would imply the Kakeya set conjecture in dimension n.
Okay. So,
Yeah. And that's EF. EF is the sum of, can be, by an idea of Jean-Bourgain, EF can be decomposed into sum of wave packets, and each wave packet is supported on the tube.
Okay. Very good. Oh, yes, please.
Silly question maybe, but is there like a sticky restriction conjecture that could be used to say something interesting?
Yeah, that's an interesting question. You can say that assume the wave packets that coming from this EF are sticky.
And then could you prove that, or?
Yeah, could you prove that? I don't know yet. Yeah, but previously when I thought about the restriction conjecture, one of the difficult toy model I had in mind is, let's assume the wave packet has one pointing in each direction. And what can we say about this? Can we have a good estimate? So that was a difficult toy model. But you just propose another toy model.
Good. Some more questions or comments? Yes.
I have a question that might be actually just a technicality that I'm missing, but in most of the proof of dilemmas, we always have, at some point we always have, especially with the constants that we're considering, we always have the, I don't know how to call it, less double tilde, so with a log delta error, and in all the final statements we don't have it. Like,
it can be absorbed by those delta to the epsilons when delta is a very small.
It can be. Okay.
Yeah.
That's true.
Good. If we don't have any more questions, so let's thanks the speaker again for the 3 lectures
Yeah, sure.
and for the last lecture.